Hello everybody, my name is Damian Aparicio-Sanchez and I'm going to tell you about the protocol analyzed with time. The first look is this online I'm going to follow for the presentation. 1. What is this talk about? The second, what is the meaning of the distant bound protocol? How works the Brands-Chaum analysis of notation? Next, adding time to the Brands-Chaum protocol. Our contribution, this contribution is our time process algebra that we use to reason the time and distance. A several distant bound protocol analyzed in the experiments, and finally the conclusions. Well, as you all know, security protocol design is a very critical task, and at the same time made very sensitive to attacks. For example of attacks, we have the famous TLS, where received a significant type of attacks. Another one is the crack attack recently in the Wi-Fi. And one of the approaches that we could use in order to improve the design of the security protocols is use the model checking as a method. With the model checking, we can prove the absence of the attacks. Also, we can find protocol weaknesses to correct the protocol. And for that, we have several analysis tools for verification of the security protocols. The modem PA, the Tamarin, and the X Aparicio, and we are going to use it for this research, the modem PA. Modem PA has the capability of the model checker. It's a tool to find or prove the absence of the attack in cryptographic protocols. Analyze infinite state of the system, has active $VAL, no abstraction of the approximation of nonce, has unbounded number of sessions. Modem PA was designed to support a very wide class of cryptographic protocols. The equational theory that he has is the Diffie-Hellman exponentiation, the exclusive OR, one approximation of the homomorphic encryption. With all these properties, modern PA make use of the unification model equational theories and the narrowing to support the backward search. Our first contribution of this paper is the connection to an SMT solver via mouth system. With this SMT solver, we can evaluate the satisfiability of the timing constraint. Well, now, the second point is what is the meaning of the distant bound protocol. First, in this type of protocols, involves two types of roles, two types of participants, the verifier and the prover. The first step for the verifier is establishes a security perimeter for all the provers, okay, the area. Next, the response delay time enables the verifier to compute an upper bound on the distance between the prover and the verifier. This is the ensure proximity, the objective of the verifier of the protocol to ensure proximity, and we use this formula for establish a security perimeter. Well, I would like to have a few minutes explaining how works the Brands-Chaum in Alice and Bob notation. The first message that the prover sends to the verifier is the commitment. And after that, the verifier sends to the prover the nonce and start to record the time when the message was sent. After that, the prover sent to the verifier an exclusive OR with the both nonce, and the verifier both messages, this one and the last one, is normally called fast response, fast message, and need the verifier to check the time and the distance for both messages for everything is correct. This is the key of the distance bound protocol. For that, if everything is correct for the time and the distance, the prover sends to the verifier the secret of the commitment and also the signature. Now, with the example of the Brands-Chaum protocol explained with the notation, we need to add in time. For adding time, we need to do three things. The first one is in the part of the sender, we need to add in a sub-index for variable of the time, and also the same for the received part. The second thing is a timing constraint associated to the metric space. The last one, we added to the D that represent the distance bound constraint of the verifier. Here we have again the notation of the protocol and the first constraint. The first constraint represents here the time for the prover sent to the message, T1, plus the distance between of them. The distance between the prover and the verifier must be equal to the T1 prime. T1 prime is the time that the verifier received the message. For the second message, the constraint, the first part of the constraint is really similar to the before for control the distance, but we add in another one. This represents that the message, for the second message, when the verifier sent to the message, this message must be sent after than the verifier received the message before. For the third message, we control these things and another one, another constraint. This is for the received part. Here, the verifier, T3 prime, must be bigger, must be before than the first message the verifier received, T1 prime. The next two messages are similar, are the same, but with different times. But we need to control, like I said before, the round trip check. The round trip check have the formula that the last message the verifier receives, T3 prime, minus the first message the verifier sent in this check fast trip, must be less or equals to multiply the distance. If this is correct, this is true, we are saying that the security perimeter is ensure the proximity with the verifier. In this case, the prover stay in a ensure proximity with the verifier. And also, when the verifier receives the secret of the commitment and the signature, he needs to check if he's able to open a commitment. If everything is okay, all the communication will be completed. Well, the next slide is about the second contribution, is the time process algebra. Our process algebra is from the modern PA. We extend it with the global clock and with the time formation. We have new syntax. This new syntax represented in the message is the add. The add in the left part we have the message, but now in the right part we have the variable of the time. The operator dot denotates sequential composition of the processes. We have the question mark for no determinate choice, and for determinate choice we have the conditional expression. For our time intruder model, we consider several located intruder, and I need to say for the $, is active. This implies intercept, forward, create message that he received. But therefore, the intruder cannot change the physics of the metric space. This metric space, like I said before in the before slides, the distance only have two arguments. One for, well, we can have the same role in the same distance, but only this metric space. All this table, all these properties for the process algebra could be used for other protocol analysis tools. Well, with all this time process algebra, we need to use it in the specification. Now, you can see the message with two parts. In the left part, we have the message, the commitment, and in the right part, we have, in all the messages, the variable of the time. We have the dot for the sequential composition of the processes. We have the determinate choice. We use this one for the round trip check, if you remember the slides before. But the verifier needs to check if the messages are in the perimeter, security perimeter. If it's true that it's secure, the verifier accepts. Then the next message is the secret of the commitment. Act with them, disable the open. If it's true, the open function, they will be received the last message of the communication that is the signature for the program. In this slide is for illustrate how the time process algebra can be transformed into the strands specification in modern PA. This is our third contribution about this paper. It's a transformation from time process into the strands with time variable and time constraint. This transformation in modern PA is also shown and complete. We have here two strands. We have the prover strand and the verifier strand. For the prover strand, the first message, the new syntax for the process algebra, we have now in the time area the arrow. The arrow represents, separate the sender information and the receiver information. In this part, the sender we have in the first argument the prover who sent the message at the time t1, and the variable as represent that will be replaced by the appropriate value that make the execution on all its time constraints possible. If we go to the verifier strand, for the first message is the commitment again, but this time is the received message. We have now in the sender information, we have that someone that sent this message at the time t1 prime, and in the right part we have the verifier who received the message at the time t1, and plus we have again the variable as that represent a set of receivers. All this new syntax, all this new process algebra into the strands mode in PA, we use for control the time and distance in the distance bounds protocol. Well, the point 6 is the experiment. We have two security protocols that have been analyzed for each protocol: the mafia fraud and the distant hijacking attacks. For the mafia fraud, where an honest prover is outside the neighborhood or perimeter area of the verifier, but the intruder is inside, pretending to be the honest prover. Using the graph, another example is an attacker to try to convince the verifier that the honest prover is closer to him than he really is. He is really similar to the man in the middle attack. The second property, the distant hijacking, an attack is possible where an intruder located outside the neighborhood of the verifier succeeds in convincing the verifier that he is inside the neighborhood by exploiting the presence of the honest prover in the neighborhood. Using the graph, the meaning of the attack is a dishonest prover, intruder in this case, located far away, succeeds in convincing a verifier that they are actually close, and he may only exploit the presence of the honest prover participant that they are inside to the perimeter area to achieve his goal. With these security properties in mind, we have encoded several distance-bound protocols in ModMPA. But for that, in this reset, we needed to include a minor modifications in ModMPA. One minor was include the subreal. Another important minor was the connection of the ModMPA to SMT solver via mod system. This is the first contribution for us. Another important thing for the experiments, although the timed model allows an unbounded number of participants, in our case, we specified one verifier, one prover, and one attacker. But we allowed an unbounded number of sessions. This table represents 9 protocols that we analyze. The symbol of the check represents the property satisfied. The symbol of the cross means that the attack was found. The times represents that the search takes the time to be complete, and the processing of the specification that eliminate the search for some probably unreachable states. Okay, and for finish the presentation, we have the conclusions. We have 3 major conclusions about this research. The first one, we have developed a timing model for protocol analysis based on timing constraints. The second one, we have provided a prototype extension of the ModMPA handle protocol with time, thanks to the SMT solver via the mod system. The third one, all this approach should be applicable to other tools that support constraint handle. And for us, the future work has several ways to extend this work. One important extension will be the full equilibrium spatial model for protocols that needs an explicit location included in the constraints. Another future work, more experiments, more distance-bound protocol will be analyzed, but another extension will be to have a larger number of participants in the specification, in the protocols. And another different future work, we can use this approach in the performance analysis. Thank you for your attention and see you in the conference.